All right, welcome. Here's our first video of the semester. This should be fun. Hopefully by now you've read that first section on our introduction to limits, so you know a little bit about what's going on, but let's just go over some definitions and things like that just to clear up some of that stuff, because it's not always really easy to exactly learn by yourself. So here's our definition of a limit. We said we're looking to see if the function value f of x, these are y value outputs over here, and we're looking to see if they get close to whatever that means. We'll talk about that. We're going to see if they get close to a certain value there as x is getting close to but is not equal to a specific x value. And this is the notation that we've got. So we've got our limit written here, and we're saying x is going to get close to some number, and we're going to take a look at what the f of x outputs do, and they get close to L. One-sided limits, the only differences that you'll notice is here in the notation, we've got a little minus sign here. Oh, that's a little thick. Let me fix that. Let's try that. Is that better? Yeah, that's a bit better. We've got a little minus sign there, and then that's for our limit on the left. The only difference there is that instead of saying but not equal to a, what we're going to say is when we're talking about a left-sided limit, we're going to say that x is always going to be less than a. And for a right-sided limit here, we're talking about x values that are close to a, but they're going to be a little bit bigger than a. So we're really just talking about on a number line. If this is our value a left-sided limit is over here on the left, and a right-sided limit is over here on the right for our x values. For a two-sided limit, normally we just call them a limit, to exist, to equal some real number value, what has to be true is that the left side and the right side both have to be equal to that value as well. So normally, if we don't really know much, what we'll have to do is go ahead and take a look at the limit on the left, take a look at the limit on the right, and just compare and see what happens. If they're the same value that we get, then that's what we'll say is our two-sided limit. So we can take a look at a graphical approximation of this. I've got a little applet on Canvas using something called GeoGebra that you can look up here. Hopefully it'll help us figure out what's going on with these limits. So let me bring that up. All right, so if you're looking on Canvas and following along, you'll notice that we're going to have to first pick an x value that we're going to approach. I'm starting at -4. We're going to look at what's going on right around here on our graph. So let's take a look at what's happening as x approaches -4. Let's start with a left-sided limit. So I'll click my left side button. You'll notice that my point here goes to the left of -4. The blue here is going to be our x value, and notice again that they're all going to be negative values here. Follow these numbers as we move things around. This is just the x and y value of the current point that we have. So right now our x value is close to -6, and our y value looks like it's right around -1. I'm going to drag this point, though, closer and closer to -4. So you'll see right now I've got an x value of -4.13 and a y value of -0.15. And as I bring that point closer and closer, we're going to see the x value change. It's going to always be less than -4. But we're going to try and figure out what the y values look like they're getting close to. Here, since our y value is -0.01, and the pattern as we move that point closer and closer is that it keeps getting a little bit bigger, we can kind of assume by looking at the graph and following the red y values here that our y values look like they're going to increase, and they look like they're going to get kind of capped by the x-axis there. They don't look like they're going to get any higher than that around this point before we have to jump over to the other side. So maybe we'll say that the limit on the left looks like it's going to be 0, because that's what it looks like the y values are going to go to. If we go ahead and start at a right-sided limit, we'll notice that our point is now on the right of that hole at -4, and we're going to bring our point closer and closer and closer and closer, and again, it looks like our y values look like they level off right at 0. So we might say that the limit on the left and the limit on the right are both equal to 0 here. And so maybe we could say that in this case our two-sided limit is equal to 0. Let's take a look at another spot. I like looking over here at an x value of 2. So we'll start with a left-sided limit again. The point is just a little bit on the right of our x-axis, and as we move it, you'll notice that we can follow what the y values are doing as x, the blue line, is going to get really, really close to 2. So we'll see what happens when we get close to 2. Looks like our y value is getting really close to 3 here. And that's what we've got over here. This y value is pretty close to 3. So maybe the limit on the left here is going to be 3. And on the right, we can do the same thing, see what happens. It looks like that y value gets really close to 0. Notice that for these limits, it really doesn't matter where this point here is defined, because we're never actually going to get to this x value of 2. So it doesn't matter if this point here is filled in or if it was open like we've got over here, or heck, if the function was actually defined down here, that's where the actual y value was at 2, because we're only looking at x values that get really close to 2. So for this one, since the left side and the right side don't go to the same y value, we could say that the limit as x approaches 2 for this function doesn't exist. So that's a bit of how we can look at things graphically. There's a bunch of examples in your text that you'll want to take a look at and make sure you know what's going on. So that's our graphical approximation. Personally, I like to draw a lot on my graphs. I like to draw some pictures with arrows and things like that. So feel free to draw a bit on those to really get a feel for where those y values are going. Now let's take a look at a numerical approximation. You're going to notice that on both of these, the graphical and the numerical, we're calling these approximations. That is not an accident. These are not going to be evaluations. We'll talk a little bit later about what those evaluations are going to look like, how to actually figure out what the limit really is. Right now, we're just making educated guesses. Let's go ahead and estimate this limit numerically. This is a cool one because we don't know a lot about this function. What we want to do is look at a limit on the left. Maybe I'll do this one in red. So for this, we want to try and get an idea for what the limit as x approaches 0 on the right of this function here is going to be. To do this numerically, all we need to do is pick some x values that are close to 0. In this case, let's do the left first. Sorry, I said right when I was doing this, but I want to do the limit on the left. We're going to pick some x values now that are on the left of 0, which means they're going to be less than 0. So maybe we'll start at -1. But what we want to do is pick ones that are going to get closer to 0. So maybe we'll do -0.5. And then we could do -0.1. And then -0.01. And we could get closer and closer and closer now by putting in more and more zeros. But let's see if this is enough. Let's check out the outputs when we take these values and plug them in here. So let's just do 1 by hand. The absolute value of -1 over 1. The absolute value of -1 is just 1. So this thing here is going to end up, oops, sorry, there's a negative on the bottom. This thing here is just going to end up being -1. Maybe we'll do one more just to make sure we know what's going on. The absolute value of -0.5 over -0.5 is going to be +0.5, because the absolute value takes the negative way, over -0.5. That's a number divided by itself, but it's negative, so it's -1. And here we're going to get the same thing. The absolute value on the top is going to strip away the negative sign, and so it's going to be positive over a negative, so it's going to be -1 and -1. These are all going to end up being -1. So we could say that the limit on the left is -1. Let's take a look at the limit on the right then. We'll do the same thing. We'll look at the limit as x approaches 0 on the right now of the absolute value of x over x. And we'll make a little table. I'll just call this f of x now. Apparently that's what I'm calling this function here. And we'll do the same thing, but now we'll pick a number that's a little bit bigger than 0, like maybe 1. And then we'll pick something that's even closer to 0, like half. And then like 0.1 and 0.01, and we could keep going if we wanted. Let's plug this in and see what happens. You'll notice that since all these are positives, that absolute value doesn't really do anything. It just leaves it positive. So this is going to be 1 divided by 1. It's going to be half divided by half, 0.1 divided by 0.1, 0.01 divided by 0.01. This function is just going to be, this limit, is just going to be on this side. All these y values are going to be 1. So we could say the limit on the right is going to be +1. Since the limit on the left and the limit on the right don't equal each other, what we'll say is that the limit as x approaches 0 of the absolute value of x over x does not exist, since the left and the right don't match up. If they did, then that's what we'd say our limit would be. Now, again, this is an approximation, and it's because we have to guess at what this pattern is going to. Now, in this case, it's pretty easy. We can see that all of these are -1, and we could make a pretty good argument to say that they have to be -1 because the absolute value is going to make whatever this number is positive, and then it's going to divide it by the negative version. So we can really justify this limit on the left, and the same thing for the limit on the right. For a lot of these, though, instead of being the same number, it might end up having changing values that look like they're going to get close to something. Like maybe we're going to get like 0.9 and then 0.99 and 0.999 as our outputs, and we have to fill in the blanks and see what that pattern is going to go to. We can make a pretty good guess that it's going to go to 1, but it's just a guess. Maybe it's going to like some weird number like 1.002, and we just had to do a couple more steps in it to really see what the pattern was. So these are all going to be guesses. Sometimes they're really good guesses. Sometimes they're not as good guesses. If we wanted to make a better guess than what we've got, then all we have to do is pick an x value that's even closer to the x value we're approaching. So we can always make good guesses here, but they're going to be guesses. So this is our numerical approximation. Now, the question is, if these are just approximations, how do we actually evaluate these things? How do we get an exact answer without any guesses, without any work here? We're going to start with these 2 easy limits, and then there's a bunch of properties of limits that you'll be able to know and learn that will help us figure these out. These I call easy limits because they're going to be pretty easy. This here is going to be a constant function, k. So let's take a look at an example, like maybe the limit as x approaches 2 of, 5. We'll see what that is. Let's just think about what the graph of y equals 5 looks like. We've got this horizontal line up here, and whether we're getting close to an x value of 2, or if we're not close to it, the whole point of this constant function is that it's constant no matter where we go on this line. The y values are all the same. They're going to be 5. So if x is getting close to 2 or not close to 2, it doesn't really matter. Our output's going to be 5. So for our first easy limit, the limit as x approaches a of any constant is just whatever that constant is. So I could put a bunch of examples on here, but it's all the same thing. If x is approaching 2 on the function 7, then that limit will be 7. This one's a bit weird. Let's take a look at an example really quickly. Let's say what happens as x approaches 2 again for x. In this case, our function is y equals x, which is the identity function, which basically just spits out the same y value as whatever input you gave. So what we have to figure out is what happens when x gets close to 2 to our function values. When x is getting close to 2, our function values are just going to be those same inputs. And so if x is getting close to 2, then x is going to get close to 2. That sounds weird to say, but since the y values are just spitting out whatever our input is, if we put in numbers close to 2 on the left, like 1.999, our y value is going to be 1.999. And if we pick an x value that's even closer to 2 on the left, then our y value is going to get just as much closer. We could do the same thing on the right. So here, if x is approaching a for this constant function x, we'll just say that limit is a. So what we can do is basically take this and plug it into our answer. What I'm going to do actually is say we're going to plug this in for x in our in our identity function. So constants just stay whatever that number is. For the identity function, you'll take this value and plug it in for x. There's a bunch of properties in your textbook, properties of limits, that basically tell us we can add, subtract, multiply, and divide these things. What they really do, though, is they tell us that we can do limits like this really easily. Let me show you how really quickly. Let's do it on this one here, just for fun. What we can do is split this limit up by basically saying when you have division like this, you can take a limit on the top and divide it by the limit of the whole bottom. And then what you can do is say that this limit of the top is like if we took this coefficient here and brought it right out in front of the limit. Basically, the reasoning is this. You can split it up into 2 limits multiplied together. These two limits are our easy limits because this is a constant and this is the identity function. And over here, we'll do the same thing. I'm going to pull the 3 out front. You'll see why in a second. And then I'm going to split the sum up. So this limit is really just 2. This limit is really just 3 because we can take this value and plug it in for x. These constants are always going to stay constants, so we can pull that coefficient out front. Really, this is the limit as x approaches 3 of 3, but we know it's going to be 3. For this one, we'll put 3 in for x, and then this guy is 1. So what we're left with is 2 times 3 over 3 times 3 plus 1, or we can say 6 over 10, 3/5. Now what you might notice is that we can skip all the way to the end by taking this value and just plugging it in for x. We're going to call these types of limits easy limits, when you can just plug them in for x and see what happens. So let's do this one here. Let's plug in 2 and see what happens. 2 cubed is 8 minus 10 plus 1. That's going to be negative 2 plus 1 is negative 1. We already did this one with our 3/5. This one's a bit weird. Square roots work out fine. We just have to be careful around 0 under there because we're not allowed square roots and negatives, so getting close to 0 is a little tricky. Let's throw that in there and we'll see what happens. This gives us the square root of negative 1 squared plus 4, which is the square root of 5. And I'll just leave it like that. That's what this limit is. Our textbook goes in and talks about how we can deal with polynomials and rationals. Basically, things with polynomials and rationals are relatively easy. We'll be able to just take this x value and plug them in. Polynomials, again, are functions like these where it's just x's with exponents and coefficients out front, and then rationals are things where you got a polynomial over a polynomial. Here, the polynomial is underneath the square root, but it makes it pretty easy as well. So make sure you go over those in your textbook, see how that all looks, but those end up being relatively easy. Here is where we get a little tricky. We can take a look at something like this and try plugging in this value to see what we get, but we're going to notice that if you do, you're going to get 9 minus 21 plus 13 by just plugging in 3 for x. And then over here, we've got 9 minus 9. Oops, sorry, this is supposed to be 12, not 13. That's going to be good, or else it wasn't going to do what I wanted it to do. There we go. 9 minus 21 is negative 12, plus 12 is 0, and 9 minus 9 is 0. So here we tried plugging this in, but we'll notice that it's not easy enough for us to just get a real number. If we get 0 over 0 when we try plugging it in, we're going to call this an indeterminate form. The function might not exist here, but we're not really sure about what's going on with the limit. Every now and then people will say that this limit is going to not exist because we divide by 0. But then some people will say the limit's going to be 0 because you have 0 divided by something. Sometimes people will say it's going to be 1 because you got a number over itself. This thing is going to be our indeterminate form. If you're following along on that rules chart that we've got up on Canvas, I think this is the first thing to fill out on the second page, that limit side. So if you printed that off or if you're just looking at it on Canvas, this is something that you can fill in here. These don't end up being too hard. What this is going to essentially tell us to do is to do algebra. We have to figure out what kind of algebra we're going to do, but in this case, and in a lot of cases, you're going to notice that your knee-jerk reaction is probably to just factor this thing. Let's factor it and see what we get. X squared minus 7x plus 12, that's going to be x minus 4 and x minus 3. And on the bottom, we've got that difference of squares. So we've got x plus 3, x minus 3. You'll notice that these two things cancel out. In algebra, what we would do is we'd say that this function looked like this now. We'd make a little note off on the side that says we still aren't allowed to put 3 into this function because in our original function we had x minus 3, and so maybe there's like a hole going on in our function. Since this limit is just what's going on as x approaches 3, not as we ever get there, we really don't care about this domain restriction. So we can say this is the same thing as the limit as x approaches 3 of this function. Technically, this is a different function than the one that we started with. It's a factored and simplified one where we don't care about this domain restriction, but the limit is going to end up being the same thing. This is one of our easy limits where we can take 3 and just try plugging it in for x. You're going to notice you won't get this 0 over 0 anymore. You're going to get 3 minus 4 over 3 plus 3, negative 1 over 6. That's our limit. So in some cases, you can just plug your x value into your function, and if you get an actual real answer, great, you're done. That's your limit. If you don't, and you get this indeterminate form, 0 over 0, then the key here is we're going to have to go do some algebra. A lot of times that means just factor and see if you can cancel stuff out, and then try it again. That's really all we've got in this section. There are a bunch of limits on here that you're going to want to try. There are a bunch of things where you're going to have to take a look at the left side and right side limits with piecewise functions where you'll have to sort out what kinds of numbers are on the left. Take a look at the domain pieces on there to see what's going on. But give some practice to these problems and we'll go on from there.